Now, we proceed with some more tests. Okay, which in this part of the lesson, we will cover the integral test and the t-test. Okay. So, we first define um, Theorem 10, which establishes the integral test. So Theorem 10 states that if f is positive, continuous, and decreasing for x greater than or equal to 1, and that an are the terms of or are the function values of f of n. Okay. Then the series, okay, whose terms are a sub n, and this integral, okay, either both converge or both diverge. Okay. So this is parang this is the illustrative proof of that theorem. That is these terms a2, a3, and so on are the function values, okay, of your function f of x. Okay. Now, one thing that you have to remember before applying theorem 10, the integral test, okay, is that number one, f of x should be positive. Okay. Number two, it is continuous. Okay. And number three, we're talking about f of x, not an. So we're talking positive, continuous, and decreasing. Okay. So these are the three things that needs to be satisfied first before you apply the integral test. Okay. Now, so going back, this a2, a3, a4 are function values of your f of x for n. Okay. So it's either this case or this case where you either inscribe rectangles or you overlap them. Okay. But in both cases, since basically summation, okay, or integration is actually a summation operation. You may be able to recall in your integral calculus course that you were using integration to find area and volume of different shapes. Okay, you use integrations to find areas and volumes. Okay, areas of plane figures and volumes of solid figures. Okay, so basically, the idea that you integrate under this curve is actually finding the sum. Is actually finding the sum of this or finding this area. Now, if it turns out that this area is actually a finite or is a finite number, if this area under this curve is a finite number, okay, it turns out that the sum, okay, for the series an would also have a finite sum, but not necessarily that they are that this area and the sum of an are equal. Okay, they are actually not. Generally, they are not. Okay, we just say that if this is a finite if this area is a finite quantity, okay, then the sum of the series will also be a finite will also be a finite sum. Okay, so that is how we illustrate the use or the proof of your integral test. Okay. So again, before you apply the integral test, make sure of these three things that is true about your f of x. Okay. The process is this: you start with an, you make it f of x. Okay, and then you determine whether f of x is positive. Okay. Two is it continuous? And number three, this is decreasing. Also, make sure that f of x is integrable. Okay, that's the most important thing about that's the most important thing about um, f of x when using integral test. That you actually have an f of x that is integrable. Uh, it's not uh, really that parang hindi maganda na we are trying to use the integral test if we cannot integrate f of x. Okay, or if we will be having difficulty integrating f of x. Okay, so yeah. Now let us, for example 14, let us determine whether the series this series converges, okay, using the integral test. Okay, first, okay, we first convert this to f of x as x over x squared plus 1. Okay. Now, for positive x, okay, or actually for x greater than equal to 1, that's where our sequence begins, eh. Okay, so for x greater than or equal to 1, okay, we see that this quantity is positive and continuous. Okay, so therefore, satisfy natin yung first two requirements niya. So it is positive, okay, and it is continuous. Positive because if you substitute positive numbers for x here, then the function is positive, okay. And obviously this is continuous because there is no condition naman that would make it discontinuous at one point, okay. But the third criteria, which is if it is decreasing, is something that we have to determine by getting the first derivative. Okay, by getting the first derivative of f of x. Okay, the function is decreasing if its first derivative, okay, is negative. Okay, so we have to make sure that in this interval, okay, this interval, the first derivative of your function is actually negative. Okay, so we first get the first derivative of this okay, we first get the first derivative of this function. Okay, so we have f prime of x equals x squared plus 1 square. So this is low d high x squared plus 1 times the derivative of x, okay, minus x times the derivative of this one. So this is 2x. This is 2x. Okay. So which is now basically negative 2x or negative x squared plus 1, okay, divided by x squared plus 1 squared. Okay, this two doesn't cancel each other out. But clearly, say for example, for x equals 1, okay, this is 0. Okay, this is 0. But for x equals 2, this is 4 times negative, so that's negative 4 plus 1. That's a negative number. Okay, so if you actually increase x furthermore, okay, you would find that f prime of x is generally negative for x greater than equal to 2. Okay, so ayun. So it means that actually except for for 1. Okay, for x you can also think about this, that if x is greater than 1, except 1 lang kasi when 1 it's 0. Okay, for x greater than 1, your first derivative is 0. Okay, so that now that now says that your function is decreasing for this range, or for this interval. Okay, again, a function is decreasing if its first derivative is negative. Okay, so for a certain values of x, when the first derivative is negative, your function is decreasing. So we were able to satisfy those three criteria, that your f of x, which is x over x squared plus 1, is positive. Okay, it is positive. Okay, number 2, it is continuous. And number 3, it is decreasing. Okay. But actually, before you actually painstakingly obtain the derivative and jump into conclusions that you would want to use an integral test, you would have to first to recognize if this is something that you can integrate easily. That's one thing that you have to remember here. As I am informing you before, you need to determine whether this is integrable to you. Okay, this might be integrable, but this might not be integrable for you. Okay, so that's the thing you have to recognize first. Okay, so now we will now proceed with integrating this one. Okay, so we apply the theorem 10 by integrating f of x from 1 to infinity. Okay, and here's the thing now. again, as I mentioned before in your previous lesson in Laplace transform, I remember that this is an improper integral. Okay. And you should be able to get around this one. Okay. You should be able to get around this by actually evaluating the limit of this integral. Okay. Or evaluating the limit of 1, and then let's put in a variable here, b. Okay. As b approaches infinity. That's how we work on this integral. Okay. So let's proceed with that. So we have the limit of the integral of x over x squared plus 1 dx from 1 up to b as b approaches infinity. Okay, so how do we integrate this one? Okay, so we see, okay, we recognize first that we can let u to be x squared plus 1, so that its differential is 2x dx. So here, this part of the differential is actually already here. That's x dx. Okay. And what is missing is actually this 2. So we can actually go around that by writing 2 here and then multiplying this by 1/2 so that this becomes 1 and we still have our original expression. Okay. And you recognize this form as actually the integral of du over u. Okay, which is the integral of u. Its integral is actually ln of u plus c. So we apply this here. Okay, so we have here the limit of 1/2 times this integral, okay, is basically ln, the ln, or the natural logarithm of x squared plus 1, okay, from 1 to b as your b approaches infinity. Okay, so this 1/2 can be taken out of the limit. Okay, so we will have 1/2 times the limit of let's put in some rule lines na. Okay, 1/2 times the limit of this is the natural logarithm of b squared plus 1 minus the natural logarithm of 2. Okay, as your b approaches infinity. Now, clearly, this becomes 1/2 times the limit of the natural logarithm of b squared plus 1 as b approaches infinity minus 1/2 times the limit of the natural logarithm of 2 as b approaches infinity. We don't have a problem with this one because this is simply 1/2 ln, or 1/2 times this simply evaluates to okay. That simply evaluates to 1/2 times the natural logarithm of 2. Okay. But here's the problem. We are actually being asked to evaluate the natural logarithm of an infinite number here, which is basically an infinite number. So therefore, we can conclude that this integral, okay, okay, this one, or the integral of f of x dx from 1 to infinity is infinite. Okay. And therefore, this means that this integral is divergent. This would imply this integral being infinite means that this is a divergent integral. Okay, and according to Theorem 10, the integral test, okay, since your integral, okay, diverges, so is the series. Okay, so we conclude that this series, okay, this series is a divergent series. Here. Okay. We would be able to conclude that this series is a divergent series. Okay. So that's how we apply the integral test. Okay. So you start off with writing the nth term of the series as a continuous function. Okay. Then or as f of x. Then determine whether that f of x is positive, continuous, decreasing, and integrable. That's the most important part, is integrable. Okay, you can easily integrate it. Okay. Because there's no use of us in using the integral test if it turns out that f of x would turn out to be an integral that is very difficult to evaluate. Okay, so therefore you really need to be very careful first with recognizing whether that series can actually be or the convergence of that series can actually be tested using the integral test. Okay, because there's no point in us in evaluating a very difficult integral. Okay, so let's proceed with example 15. So let's determine whether this series is convergent or divergent according to theorem then. So again, we start off by having f of x equals 1 over x squared plus 1. Now, obviously, for x greater than equal to 1, this is positive. Okay, that is positive. That is a positive. Um, that is a positive function. Okay. Number 2, that is also a continuous function. Okay. Okay. Now, number 3, if this is decreasing. Now, since the numerator is a constant, the denominator is something that is that is changing. Okay, and as you can see, as you increase x, the denominator is also increasing. So in that case, if the denominator is increasing, the tendency for f of x is actually decrease. So as you increase your f of x is decreasing. Is decreasing. So therefore, we can conclude that f of x is a decreasing function. Okay, without actually getting the derivative na. Okay, you can actually verify this using differentiation. Okay, by um determining whether f prime of x is negative for x greater than equal to 1. Okay, you can do that. Okay, but if if it is possible that you can do that by inspection, if it is possible that you can determine whether a function is decreasing or not, okay, by inspection, then by all means do so, because that makes that makes our solution more efficient. Okay, again, the only question that we would like to answer is whether the series um is convergent or not. Okay, and we don't really want to spend more time working on some things that would just be tangents to that question. Like for example, if this is really difficult to be differentiated, okay, probably there's no point of you differentiating it if you are able to reason out that this function is decreasing. So tulad nga ng sinabi ko, just what I am pointing out, I can I can say that this function is decreasing. Okay. I can argue that this function is decreasing because if I am increasing x in this interval, okay, so you can see that x is actually greater than a number. So it means that your x is actually a number that is increasing. Okay. So if you're actually increasing x, given that the numerator is constant, then the denominator here is increasing. Okay. And this ratio is actually getting lower and lower in value. Okay, because its denominator is increasing. So by virtue of that, okay, I can be sure that this function is decreasing without performing the the differentiation. Okay, so if you can argue that way, that's fine. Okay, that's a valid argument. And that's a valid way of finding because you don't really want to spend your time doing the differentiation where in fact you are trying to answer a different question. Okay, so we are now able to see that this function is positive continuous decreasing, and I can I can recognize a form which when I integrate this I can be able to integrate this one. Okay, so since these three requirements of theorem 10 have been satisfied, we will now proceed with integrating your f of x from 1 to infinity. So we have here the integral of 1 over x squared plus 1 dx from 1 to infinity. Or that's basically the limit of 1 over x squared plus 1 dx from 1 to b as b approaches infinity. Now, this integral is simply the arctangent. Okay. So this is the limit. This integral is the arctangent. So this is the arctan x from 1 to b as your b approaches infinity. So this is the limit of arctan b as b approaches infinity. Okay, minus the other half of this definite integral is basically a constant. So I don't need to write the limit as required. Okay, because that's basically a constant. This is simply arctangent of 1. So the limit of arctangent of 1 as b approaches infinity is simply arctangent of 1. Okay, which is basically pi over 4. Okay. So the arctangent of 1 is pi over 4. You can try that out with your calculator. But remember to set your calculator in radians. Okay. But how about the limit of the arctangent of b as b approaches infinity? Okay. Remember that your tangent function, okay, your tangent function, okay, approaches infinity when this angle is 90 degrees or pi over 2. Okay. Remember that cosine pi over 2 is 0. Okay. And sine pi over 2 is 1. So 1 over 0 approaches infinity. So therefore, tangent pi over 2, okay, is approaching infinity. So therefore, its inverse, that is the arctangent of a very large number, okay, approaches pi over 2. So therefore, this limit can be evaluated simply to pi over 2. Okay? And therefore, pi over 2 minus pi over 4 is simply pi over 4. Okay? So this is what it implies. The integral f of x dx from 1 to infinity has a finite or evaluates to a finite number. Okay? It implies that f of x, this integral, is convergent. Okay? Since this integral evaluates to a finite number, it means that this integral is convergent. Okay? Therefore, by Theorem 10, okay, the sum an for n equals 1 up to infinity, which is your summation of 1 over n squared plus 1, okay, is also convergent. Both of these should converge according to Theorem 10. If this converges, then also your series would converge. Okay. For example 1, okay, for this example, since this integral diverges, and so is the series. So the series is also divergent. Again, Theorem 10 states that both of these should diverge, okay, or both of them should converge. Okay, so that is example 15. Now, let's talk about p-series and harmonic series. Okay, so in the remainder of this section, we will investigate a second type of series that has a simple arithmetic test for convergence or divergence. Okay, so a series of the form, such as what you can see here, okay, is what we call a p-series. Okay, it's a recognize how p-series evolves now. It's actually 1 over n raised to p. N is your index, okay? N equals your index here, okay? So p is a number from 0 to any number, okay? So, for example, when p is 1, okay, for p equals 1, your series, okay, becomes that way. Okay, so this is 1 plus 1 half plus 1 third plus 1 fourth plus 1 fifth and so on. Okay, when p is 1 half, okay, the series becomes Okay. 1/2 raised to n raised to 1/2. Okay. Or basically, that's the sum of 1 over square root of n. Okay. When p is 1/2. So that when you expand this, this becomes 1 plus 1 over square root of 2 plus 1 over square root of 3 plus 1 over square root of 4 and so on. When p is 2, when p is 2, that series becomes the sum of 1 over n squared for n equals 1 up to infinity. So that should give you 1 plus 1/4, okay, plus 1/9 plus 1 over 16, okay, tama, 2, 3, 4, 1 over 25, and so on. So those are P series, okay? Those are real P series, okay? We have a special name for this one, okay? When P is equal to 1, we call this the harmonic series, okay? And that the name harmonic series has something to do with with sound, okay, with vibration. So any application that that involves sound and vibration, okay, has harmonics in it. So basically, okay, basically that name, that harmonic series name or term was derived because this series can actually be applied to those applications. Okay. So yeah. Now, the general harmonic series, okay, is of the form of this one. So we have here a scaling factor and a term, okay, added to the scaled n. Okay. So again, the name harmonic has something to do with music, sound, uh, vibration of strings. Okay, so yeah. So there is a very simple test. Okay, if you can recognize that a series is a T series, okay, there is a very simple arithmetic test using Theorem 11 to determine whether a P series converges or diverges. Ito lang yan. Okay. Okay. A P series converges if P is more than 1. But if it is between 0, okay, and 1, your P series diverges. Okay, so in this case, I have given here three P series. When P equals 1, P is 1/2, and when P equals 2. Of all these three, okay, this is divergent because, again, P between 0 and 1, divergent, the P series is a divergent series. And when P is greater than 1, your P series is a convergent series. So therefore, this is a divergent series, this is a divergent series, okay, this is a convergent series. Okay, so there, that's a very simple, Theorem 11 provides a very simple arithmetic test to determine whether a P series converges or diverges. Also, I would like to take your attention back to this series. Okay, this summation of here, ito pala yun. This harmonic series, okay, which is have been discussed in the previous lesson. This is the last example of the previous lesson. Okay. You can see here that this is we actually had to use the divergence the n term test for divergence, okay, in which we determine that the limit of although the limit of 1 over n as n approaches infinity is 0, okay, we won't be able to say that this is convergent or divergent. And when we try to get a plot of the partial sum, okay, when we try to get a plot of the partial sum of this, okay, uh, turns out that the series is divergent. Here's the reason. Here is why we can say definitively now that that series is a divergent series. That series is actually a P series, okay, with P equals 1. And when P equals 1, for a P series, when P equals 1, that series becomes divergent. Okay. This is the third example that I have given here. Okay. So this is a convergent series according to theorem 11. Okay. Now how about this? Let's determine whether the following series converges or diverges. So we start off with because this is neither this is okay, there. This is not a P series. Okay, you can see that this is not a P series. But later on, we will have a method in which we will be comparing two series. Okay, in which if one series converges, we can deduce or we can apply some theorem that can actually make us conclude that the other series converges. Okay, so we will discuss that in a later topic. Okay, but let's take a look at this one. Now, since this is a series that that looks like not a P series. Okay, so we turn to to the integral test. Okay. So we start off by writing this off as f of x equals 1 over x ln of x. Okay. Now, let's determine whether this series is positive. Again, for x greater than equal to 2. Saan ko nakuha yung 2? Here, in limit, lower limit. Okay. Where do we get that 2? That lower limit. So, it is positive. Okay. Because ln of x is a positive function. The natural logarithm of x is a positive function for x greater than 1. Okay. It becomes only negative when x is fractional. Okay. Now, we say that this function is continuous. We dare say that this is continuous, okay, without proof. But it can be easily be proven, but we know that this is continuous. Okay. And number 3, we would like to know if this is decreasing. Okay. Now we know that ln the logarithm the natural logarithm function is an increasing function, but we don't know how it behaves. Obviously, if it is if we take its reciprocal, okay, if we take the reciprocal of the natural logarithm function, it would be a decreasing function. But here kasi it's multiplied with x. So it's more or less again, if x is increasing, then the more that this would be a decreasing function. Okay. So that can be definitively proven by actually getting the first derivative, okay? By getting the first derivative of your function, okay, which is negative, obviously negative, because if x is greater than equal to 2, this is positive, okay, this is positive, this is also positive, but your fraction is negative. So if this ratio evaluates to a positive number, but there is a negative but that needs to be multiplied to a negative number, negative to negative 1, then the function is this derivative is negative for x greater than equal to 2. Okay, but again, you can argue it this way. Um, we can argue it this way. Okay. The product x ln x is an increasing function. You can say that with conviction. Ln of x is an increasing function. Multiply that with x, it would still be an increasing function. In fact, it would increase faster. Now, take its reciprocal. It means that if you are getting if you are increasing your denominator with a constant denominator, then its resulting function is actually decreasing. Okay, so without taking the derivatives, I can argue that f of x is a decreasing function using this argument. Okay, so now evaluating the integral, okay, you can rewrite 1 over x times the natural logarithm of x in this manner. It's 1 over x times ln of x dx. Okay. So why did we, why did we, uh, why did we do that? Okay. We recall that if we let u to be the natural logarithm of x, its differential du is dx over x. Okay. So as you can see, this is du, this is your u. So this is in the form of du over u. Okay. And its integral is the natural logarithm of u plus c. Okay. But u is the natural logarithm of x. So therefore, you would have something like this as its integral. Okay. And therefore, again, applying the limits. Or since this is an improper integral, we transform it into a limit problem with the limits being b and 2. Okay. Now, this part, the limit of this part is obviously infinite. Okay. While this is a constant. So this is simply the natural logarithm of the natural logarithm of 2. Okay. But the other half is actually an infinite number. So therefore, eventually, this number becomes an infinite number. So since your integral of f of x dx from 2 to infinity diverges by theorem 10, ano ba? Yeah, by theorem 10, by theorem 10, okay, this series would also diverge. Okay. But there is an interesting thing about this series. If you actually generate the sum or the partial sum of this series, um, this series actually diverges very, very, very slow. Okay. Um, if you add the first 10 terms, you would have 1.68 something. Okay. But adding first 100 terms, that's 90 terms more. Okay. We just increase the sum to around 2.3. So that's around 0.7. Okay. That's around 0.7 increase. Tama. 1.68. Yeah, 2.3, something like that. 0.60 something. For 90 terms, ah. Okay. And if you actually generate write a program write a program or write a script on MATLAB about this and try to find the sum of the first 10,000 terms, you can only have 3 point something as its sum. It is increasing, indicating that it is divergent, okay? But it is increasing very, very, very slowly. Okay? It increases very slowly. Okay. If you're interested, you may find the sum of the first 100,000 terms, and I would suspect that this would just amount to around 10 or 9. Okay. Just two digits. Okay. So something like that. Okay. So here in this lesson, we have covered the integral test and the p and the divergence or convert and the conditions for the divergence and convergence of AP series. Okay. In the next topic, we will cover some more tests.